evening, friends. While analyzing any flow problem, any problem of flowing fluid, the aim is to describe the motion of the particles, maybe by Euler or Lagrangian description, and to analyze that what are the forces acting on the fluid elements when they are moving. So solution of any problem begins with finding out the velocity vector function of that flow field. So suppose there is a space like this, and I am describing this space by Cartesian coordinate system x, y and z. Now in this space some fluid is moving, so I want to analyze this flowing fluid. So first step will be to find out the velocity as a function of this particular location x, y, z and time. So in this regard there is a scalar function known as the stream function which can help us, and this function was derived by Lagrangian while solving the flow problems in curvilinear coordinates. Though his problem is specific to two-dimensional systems only, two-dimensional flows only, but later on Stokes gave another stream function which can be used for three-dimensional flows also. But we need to remember that stream function is defined only for incompressible fluids. Okay, so please remember, whatever we are going to do, that is for incompressible fluids. And since we are more concerned about gate examination, so we will talk about the Lagrangian definition of the stream function. Now this function can help us plot the streamlines in the flow field, and if you remember, the streamlines are imaginary lines which give us the direction of velocities of different fluid particles at a particular instant of time. Now if the flow is steady, then streamlines also become the path line, okay? And the stream function also helps us to describe the flow velocity components. So let us first of all see that what is this mathematical postulation of stream function, and later on we will discuss the properties of the stream function. Mathematical definition of the stream function can be obtained from continuity equation, and we are going to study the case that was considered by Lagrangian himself. Okay, so what the assumptions are that we have some incompressible fluid which is flowing steadily in a two-dimensional manner. So two-dimensional manner means that the flow properties like velocity, acceleration and pressure can be described by only two coordinates. They are function of two coordinates only, maybe x and y, and their derivative, their gradient with respect to third coordinate z will be 0, right? So for these cases, if you remember, the continuity equation, that is the mass conservation principle, can simply be written as del u by del x plus del v by del y is equal to 0, right? U and v are the velocity components along the principal directions x and y, while the third component w will be 0 because this is a two-dimensional flow. Now let us assume that there is some kind of function f such that del f by del y is equal to u and del f by del x is equal to negative of v. Okay, now u and y, these are scalar quantities because these are velocity components along particular directions. So f is also a scalar function. So let me assume that there might be a function like this. Now if f exists, that is, these definitions are valid, so when we substitute these quantities into the continuity equation, into the left hand side of the continuity equation, the left hand side should become 0, right? The continuity equation must be validated. So let us see, if we substitute these values into the left hand side of the continuity equation, whether the continuity equation is valid or not. Okay, so I am considering the left hand side only. So once we substitute u, it becomes del by del x of u, which is del f by del y, plus del by del y of v, which is minus del f by del x. So this becomes what? This becomes del square f by del x del y. This becomes del square f by del x del y minus will come out, del square f by del y del x. Since the two terms are equal on the basis of calculus, this minus sign means that the left hand side becomes equal to 0. So left hand side and the right hand side of continuity equation are being validated, are equal. Therefore f is going to satisfy the continuity equation also. This means that the f the scalar function f will exist. Now this function f, we call it as the stream function, and we shall write it as psi. Okay, so from this mathematical analysis, what we can define, we can say that whenever the flow field is going to satisfy these assumptions, then there exists a scalar function psi, which is function of x comma y, such that del psi by del x, if you remember del f by del x, so del psi by del x is equal to minus of v, and del psi by del y is equal to u. So this is the mathematical definition of stream function particular to this case. Okay, now let us see that what are the properties of this stream function. So stream function is going to follow some properties which are very important in using this mathematical postulation to solve our problems. And the first important property is that the stream function is constant along a streamline. Okay, so if you remember, streamline is an imaginary line which gives us the direction of velocities of different fluid particles but at same instant of time. Okay, please remember this. So this gives us the definition of streamline, and that definition simply becomes that dx by u is equal to dy by v. Okay, so this is the definition of streamline. Now let us jumble this equation a little, and what we get is v dx equal to u dy, or we can also write u dy minus v dx equal to 0. Okay, so whenever we are going to describe streamline, then for the streamline, this equation is going to be valid. Am I right? Now let us move back to the definition of stream function. So we said that stream function is a scalar function of x and y such that del psi by del x, the partial derivative of psi with respect to x, is equal to negative of component of velocity in y direction, and del psi by del y is equal to component of velocity along the x direction. So this is the mathematical definition of psi. Now psi is a function of x and y. Okay, so if I am going to take a total derivative of psi, what I can write it as d psi is equal to del psi by del x dx plus del psi by del y dy, right? Now what is del psi by del x? So from the definition we get it as minus v dx. What is del psi by del y? So this is u. So u dy. Therefore total derivative of psi is equal to minus v dx plus u dy. What this means is that let us suppose we move from one point to the other in the flow field. Then the change in stream function because of this movement is given as minus v dx plus u dy. Okay. Now consider the right hand side of this equation and the left hand side of this equation. So this becomes what? If we compare those two equations, what we can say is that d psi is equal to 0. But this is the equation of a streamline. This means when we move from one point to the other and those 2 points lie on the streamline, then the change in stream function is 0. So this means what? That psi is equal to constant, but for the 2 points which lie on a streamline. Right? So stream function becomes constant along the streamline. So this is a very important property, and based on this property we can even analyze the discharge through a cross section of the flow field. Okay, so let us move on to the second property now. The second property of stream function is specific to irrotational flows, that is potential flows. And if you remember, irrotational flow means that the angular velocity or the vorticity is going to be equal to 0. And if you remember the definition of mathematical expression of angular velocity, then for two-dimensional flow, the angular velocity is simply this. Am I right? Now if the flow is irrotational, the angular velocity is going to be equal to 0, and this means that del v by del x minus del u by del y is going to be equal to 0. Right? So whenever the flow is irrotational, that flow will not only follow the continuity equation, but it will follow this particular equation also. Now previously we described stream function, and we said that since stream function is going to satisfy continuity equation, therefore it is going to exist whenever the fluid is incompressible, right? Now let us try to substitute stream function in this equation into the left hand side. Okay. Now if you remember, the V is simply minus del psi by del x, and U is simply del psi by del y. So what I am doing is I am taking the left hand side of this equation. Okay. So left hand side becomes del by del x of del psi by del x, and there will be a negative also, right? Minus del by del y of u, and this will become del by del y of del psi by del y, right? Now this is what? This is minus del square psi by del x square minus del square psi by del y square. Right? Now we are saying that when the flow is irrotational, this left hand side is equal to 0. Therefore, for irrotational flow, this will become 0. Right? And this can also be written as del square psi by del x square plus del square psi by del y square equal to 0. This means that whenever the flow is irrotational, whenever the flow is potential, the psi is going to follow this particular differential equation, and this form of differential equation is known as Laplace equation. So always remember that psi is going to follow continuity equation whenever the fluid is incompressible, and it will follow Laplace equation if the flow is irrotational. So now let us move on to the next property of stream function. The next important property of the stream function is that it helps us to find out the discharge or the flow rate in the flow field. Okay, and what it says is that let us suppose there are two streamlines, one is A and the other is B. Now corresponding to these streamlines, these stream functions have values psi B and psi A. So the fluid, the discharge flowing between the two streamlines can be calculated, and it is simply equal to psi B minus psi A. Now if you can see, I have written meter cube per second per meter in the units. So this meter cube per second gives us the flow rate, while meter means that if the flow is in the plane of the board and the flow field has a width maybe 1 unit perpendicular to the board. Okay, so per unit width, the flow field, per unit width, the discharge can be simply given as psi B minus psi A. Okay, so let us prove this. So what I have shown is that there are two streamlines A and B, and maybe these streamlines are very close. Okay, corresponding to these streamlines, the functions of stream functions have values psi and psi plus d psi. Here instead of psi B, I have written psi plus d psi because the streamlines are very close. So difference of stream functions will be less, right? Now, as per definition, the flow rate per unit width can be written as psi plus d psi minus psi is equal to psi. So this is psi B and this is psi A, right? Now let us prove this, okay? So we have shown a section between the streamlines, and through this section we are trying to find out the discharge rate, right? Now let us take the projection of this section along the x-axis and along the y-axis. So suppose if this line segment is ds, okay, then the component along the x will be dx and the component along the y will be dy, right? So now we have two cross sections. One is dy into 1 unit, right, perpendicular to the plane of the board, and the other is dx into 1 unit perpendicular to plane of the board. Okay. Now velocity components at this point may be u and v, right? So standard directions, the general directions of u and v can be defined as u going up and u going forward and v going up, right? Now what is the discharge? What is the discharge through dx? It is v dx into 1. What is the discharge through dy? It is u dy into 1. Okay. Now we have got basically a triangular element which has sides ds, dx and dy. And if you remember, the assumption of this analysis is that the flow is incompressible. So whatever fluid is coming inside this triangular element, the same amount of fluid, it has to go outside also. Now q dot is coming inside, v dx is coming inside, and u dy is going outside. So what I can write as q dot plus v dx is equal to u dy, right? Now q dot is equal to u dy minus v dx, right? What is u? U is del psi by del y, right? What is v? It is, what is minus v? Minus v is del psi by del x, right? So del psi by del y dy plus del psi by del x dx, this is equal to what? This is equal to d psi, that is the total derivative of psi. So q dot is simply equal to d psi, right? So flow per unit width between the two streamlines is equal to the difference of stream functions for those streamlines, okay? What the fourth property says is that let us suppose there are two streamlines given as streamline A and streamline B, and on those streamlines I have marked 2 points A and B. From these 2 points, joining these 2 points, I have made a random curve AOB, okay? Then the difference of the stream functions corresponding to the two streamlines is simply equal to the line integral of normal component of velocity along this curve. Okay, let us see how to prove this. So what I have done is that on the curve AOB, I have taken a very small line element ds, and the tangential to ds is along this direction. Now corresponding to this ds, the actual flow velocity was given as v. So I have resolved this v vector into two components. One is along the tangent and the other is along the normal to ds, right? Now if you remember, the discharge through any section is equal to the normal flow velocity into the area of the section, right? Now let us take this element ds. So ds into 1 unit width perpendicular to the plane of paper. So discharge will simply be equal to normal velocity component, which is v sine theta into area of the section, right? This becomes ds. So if the if the discharge through this element is this much, then the total discharge from AOB will simply be equal to integral of AOB, right? But this means the discharge between the two streamlines A and B, and from the previous property we remember that the discharge between two streamlines is simply equal to psi B minus psi A, right? So this logic proves our fourth property, okay? So now we have 4 important properties of as well as definition of the stream function. So just to summarize, stream function is a scalar function, okay, defined particularly for incompressible flow fields. The stream function, the definition of stream function that we have given is particularly for two-dimensional flow, okay, and that is that del psi by del x is equal to u, and del psi by del y, del psi by del x is equal to v minus v, and del psi by del y is equal to u. Now this definition helps us to plot the streamlines as well as to describe the flow velocity components as functions of x and y, right? Now important properties are that along the streamline a stream function is constant. Between two streamlines, the discharge is given by the difference of the stream functions, and the stream function is going to follow Laplace equation whenever the flow is rotational, though stream function is always defined because stream function is going to follow the continuity equation. And the fourth important property is that the difference of two stream functions is equal to discharge between the two streamlines, and it is also equal to the line integral of the normal velocity components, okay? So this is what is all about stream function, which is important to us for the GATE examination. Now in the next video, we will solve 1 or 2 questions from the GATE examination related to stream functions. Thank you.